Okay, so just a couple things. Remember, I'm not here tomorrow. Out of the building. I'm going to be at a workshop. So the assignment for the lesson we just finished up, not this guy right here. This is just a preview of coming events if you're going to go into calculus next year. Okay. Hello. He's not here today. Thank you. All right. This is just going to be, like I said, a preview of upcoming events if you're going to get into calculus next year. But the homework you get tomorrow, I'm hopeful you can finish it up in class. You guys can work together, but, please work on the assignment. I don't know if the sub is going to have a math background or not, so maybe you can help each other out. Whether you do finish or not, it will be due on Tuesday, the next time I see you guys. Speaking of Tuesday, by 8:05 a.m. on Tuesday, that's the deadline if you want to retake exam 1. Okay, so I've already had several people come in. If you need to be one of those people, please come on in as soon as possible because our time is running out. When's the second exam? Monday the 17th, so a week from this coming Monday. All right, we'll be talking more about that next week as we get closer to it. Okay, so I'm hoping that you guys were able to go home and look over this last night. But when we get to the problems, I'm going to count on you to help me out because the faster we go, the more time we have for your quiz. Okay, so you guys are going to be typing in some values and helping me get those. So what are we talking about today? Continuity in behavior and limits. The graph of a continuous function has no breaks, holes, or gaps. You can trace the graph of a continuous function without lifting your pencil. So we've talked about that before, but now I just want to go a little more specific and actually analyze a value, some x. Okay, is it going to be continuous? And if not, what type of discontinuity do we have there? So one condition for a function f of x to be continuous at some value that we're calling c is that the function must approach a unique function value. Now we're talking about the y's as the x values approach c from the left and the right. And you're going to see that over and over today. The only way the limit is going to exist is if, as you approach x from both sides, you approach the same value of y from both sides. Because for every x, there should be a corresponding y value as part of the function. So the concept of approaching a value without necessarily reaching it, you may or may not, that's what we call a limit. Okay, so I'm not going to bother with this stuff right here. I'm going to go ahead and just get right into it. If there is a problem at a particular value of x, well, these could represent what's happening. We have an infinite discontinuity. That's a vertical asymptote. If, as we approach some value of x that we're calling c from both sides, the y values either increase or decrease indefinitely. That means we're going positive infinity or negative infinity, and you'll be able to notice that very quickly. Okay. We have a jump discontinuity. If we approach x from the left and the right, the limits of the function as x approach c from left to the right exist, but have two distinct values. So if we approach x from the left and the right, but as we approach y from both sides, we get two different numbers, that's going to represent a jump discontinuity. And it makes sense because we'll probably be looking at something like a piecewise function. And a function has a removable discontinuity if the function is continuous everywhere except for a hole at x equals c. Now it's important to note, and I'll show you this at the end, even though you have a hole here, the limit as you approach that value of x from both sides will still exist. Now the function may not be defined at that value of x. It may be undefined because it divides by 0 or whatever the case is, but the limit as you approach it will still exist. Okay, so all of this is probably pretty fuzzy. I'm thinking once we get into some examples, things will come into a little bit more focus. That's typically how things work in mathematics. Okay. So let's just get right into it. The continuity test. Okay, there are 3 steps here. So a function f of x is continuous at x equals c if it satisfies these 3 conditions. Now, they were bullets, but I always like to look at them as steps because I think for me that just makes it kind of easier. Step number 1 is the easiest one. F of x is defined at c. That is, f of c exists. So whatever value of x we're interested in, we just want to evaluate the function at that x. We want to see if we do get a corresponding value of y or not. Okay? So does he exist, yes or no? Number two, f of x approaches the same value from either side of c. That is, the limit as x approaches c of f of x exists. Now, we're going to be using a table to analyze these values. Okay, just a table of values. But I want to go ahead and emphasize something right here. How did I write a limit to let the reader know that I was approaching it from, say, the left or the right? Does anybody remember from our discussion earlier in the week? Okay, Satish? Yes. So how do I tell specifically the direction? Not a superscript. I'm sorry, I thought you said subscript. Yes, that's absolutely right. So if we're approaching some value c from both directions, okay, the limit as x approaches c from the left of f of x, the limit as x approaches c from the right of f of x. If in the place of a power you put a positive or a negative symbol, that tells you the direction. The negative is the left, the positive is the right. I got a text message. Okay. Now, this one here, the limit as x approaches c of f of x, if there is no positive or negative given as a power, that means we are approaching it from both directions. Now, this guy, he only exists if I get the same value from both directions. Okay. So again, that might not make a whole lot of sense right now. Let's get into an example and see what you think. So that's step 2. Now step 3, the value of f of x approaches from each side of c is f of c. That is, the limit as x approaches c of f of x should equal f of c. So whatever value you got for step number 1, if it's continuous, you should get the exact same value in step number 2. And if we don't, well then that's when we have one of those discontinuities. Okay? Well, let's try one. Determine whether f of x equals 2x squared minus 3x minus 1 is continuous at x equals 2. So here's the value of x I'm interested in. X equals 2. We want to justify using the continuity test. All right. Well, step 1, that's the easiest. All I want to do is take that value of x and we're going to plug it in. So I'm asking myself this question. Okay. Does f of 2 exist? All right. Well, let's see. 2x squared would become 2 times 2 squared minus 3x, so minus 3 times 2, and then minus 1. Okay. Well, somebody help me out. What would that be if I evaluated it? I do get 1. There we go. So what are we thinking about step 1? Does f of 2 exist? Yes, I was able to get a y value. Okay, there are no problems here. So step number 1 is good to go. Things are looking great. Now we're going to move on to step number 2. And this is where you're going to analyze the table. And you see I've already got it set up for us. So in step number 2, I want to find out, does the limit as x approaches 2 of f of x exist? Okay. Well, see, we've mentioned several times that as we approach a value of x, in this case 2, from the left and the right, we're very, very interested in seeing what the function, the y values, are approaching. So this is already set up. On the left, we have 1.9, 1.99, 1.999. So we're getting closer on the left, and on the right, we're doing the same thing. 2.1, 2.01, 2.001. So I'm going to go ahead and write out these limits for their specific direction. Okay, what symbol did I use to show from the left? Okay, so 2 from the left. As a power, I'm going to put that negative there. F of x equals. And then over here, because we're approaching it from the right, I'm going to go ahead and say 2 from the right. I'm going to use the plus symbol of f of x. Okay. Now, this is where I was talking about a moment ago. I'm really going to need your help because I'm going to rely on you guys to give me these values. So the longer it takes you to give me these values, the less time you're going to have for your quiz. I'm going to help you out with the first one. Just like we did with this 2 right here, We want to take these values one at a time, oh, not the 2, and plug them in. So 1.9, 2 times 1.9 squared minus 3 times 1.9 minus 1. If you were to do that, it should be popping up in your calculator 0.52. Okay. So now, help me out with the others. If I were to type in 1.99, what should I get? So 2 times 1.99 squared minus 3 times 1.99 minus 1. Yeah, just go ahead and tell me. There we go. So I'll just say 0.95. Perfect. Does anybody already have 1.999? So Kyle, you're saying 0.99? I would agree with that. Okay. So see, take a look. As we're getting closer to x on the left, what do the y values seem to be approaching? Looks like they're approaching 1, right? They're getting really close. So I'd say the limit on the left side is going to be 1. Okay. Now let's do it from the other side. But I always like to start at the far end of the table because you're wanting to see what it's approaching. Okay. So somebody plug in 2.1 for me. Oh, I heard 1.52. Yes. 1.52. Perfect. What if I plugged in 2.01? 1.05. Okay, let's do that. Perfect. What about 2.001? 1.005. Okay. So as we're approaching 2 from the right, what do the y values seem to be approaching? They seem to be approaching 1 as well. And this is what I was referring to a second ago. This guy right here, the limit as we approach 2, he's only going to exist if from the left and the right I approach the same number. Is that what happened? Yeah. Because on the left and the right, we're approaching 1, I can say the limit as we approach 2 is 1. So there's step number 2. Okay. Now in step number 3, we want to compare what we got. Okay. So in step number 3, I'm going to ask myself this question. Does what I got in step 1, does f of 2, that value, equal the limit as x approaches 2 of f of x? What is that noise? Is that somebody whistling? What is that? Oh yeah, let's stop that, please. Okay. So what did we get when we evaluated f of 2? What did we get? 1. Based on the table, what I get for the limit as x approaches 2 of f of x? 1. Does 1 equal 1? Yes. So what would you say about this function at x equals 2? Is it continuous? Yes. It passed the continuity test. Yes. That's all there is to it. Now, if any part of this fails, that's when you want to start looking at your discontinuities. Okay? So again, it's not as bad as we may think. Okay, limits, proofs, all that, very, very easily taken care of. Let's try another one. Okay. Now this one here, we're wanting to do the same thing. So it looks like we have a piecewise function. We have our subdomains here. Okay. 2 linear functions. The first one greater than -3. The other one less than or equal to -3. Now the x that I'm interested in is -3 itself. Okay. So let's run through those steps. Step 1, I want to evaluate the function at that x. So does f of -3 exist? Okay. Can I plug -3 in and get a y value? What do you guys think? Yes or no? Yes. Well, which one am I going to plug into? I don't remember how to do that. Why the second one? There you go. When we first talked about piecewise functions, remember, look for the interval that contains your x. So I'm going to plug the -3 right in there. So what is 2 minus a -3? That's 5. Okay, so that's all you got to do for step 1. Okay, so the function is defined at x equals -3. So far, things are looking good. Okay, now let's see what happens as we approach that -3 from both sides. Again, our table is set up for us. Here's 2. I want to show that the limit as x approaches -3 of f of x is hopefully going to be something. Okay, so let's see. So if I'm approaching it from the left, I'm going to say the limit as x approaches -3, and then I'm going to put that little minus right there of f of x. And then over here, I'm going to say the limit as x approaches -3 from the right of f of x. Okay. Now again, I'll go ahead and help you out with the first one. Okay. I've got values on the left that are slowly getting closer to -3. Now here's my question though. We're dealing with a piecewise function. -3.1, -3.01, are they greater than or less than -3? These are all less than. So for these here, I'd want to make sure to plug those into the 2 minus x. These values over here, if I'm approaching it from the right, they're all greater than. So you just want to make sure you are plugging it into the correct function, or it's going to give you something that's wrong. Okay. So if I were to plug in -3.1, well, I'm going to get 5.1. 2 minus -3.1. Well, what would happen if I plugged in -3.01? Okay, what's that, Kyle? 5.01. Perfect. What about a -3.001? Okay, 5.001. Perfect. Okay. So as we approach -3 from the left, what are the y's? What's the function approaching? Looks to me like it's approaching 5, right? 5.1, 0.1, 0.001. Yeah, we're getting closer to 5. Now, are things looking good? Because what happened to step 1? We got 5, right? Okay. Well, now let's come on over here. Somebody help me out with -2.9. Okay, -10.7. Perfect. What about a -2.99? -10.97. What about -2.999? -10.997. Okay. Now, as I approach -3 from the right, what are the y's approaching? -11. Now, again, I want to emphasize this idea. The limit as we approach -3 only exists if I get the same value from the right and the left. Is that what happened? No, they are approaching two completely different numbers. So this guy doesn't work. So there's no need for me to do step number 3. I'm not going to be able to show that I can compare steps 1 and 2 and I get the same result. So this tells me there has to be some kind of discontinuity going on here. Okay? So let's take a look at the 3 we had. Is there any discontinuity that talks about as you approach from left and right, you get 2 different numbers? Which one is that? This is a jump discontinuity. We have 2 distinct values. One is included, but the other was not. Yes. So based on our analysis, okay, I would say what's happening here is a jump discontinuity. So this function is not continuous at x equals -3. See, here's the thing. You know, when we're making these graphs, when we're talking about these rational functions, these are the things that we're seeing and we're working with. But now specifically, we're kind of going in and saying why. Okay, why we have these. How are we doing? Does anybody have any questions? Okay. Let's try another one. Okay. Now this is our first rational function. Okay. But we're going to go ahead and go through one and we'll kind of talk about the other just for the sake of time. So let's go ahead and take a look at the 3. Let's focus all of our attention on x equals 3. Okay. So we had one problem where steps 1 and 2 worked out very nicely. We had another problem where step 1 was good, but then we had a problem on step number 2. Okay. So what is step number 1 again? I always forget. What do I want to do with the continuity test? There you go. That's the first step. I simply want to plug in the value of x we're interested in. So for step 1, does f of 3 exist? Well, let's see. X plus 3 would be 3 plus 3 over x squared minus 9, 3 squared minus 9. So that looks like it's going to give me 6 over what? 0. Okay. So we have a problem already. Now, just because step number 1 fails does not necessarily mean you still won't be able to get a limit. Okay? Especially if it's a removable discontinuity, the limit is still going to exist, but the function just can't be evaluated at that x. Okay? So you still want to move ahead. Let's try step 2. I want to know, okay, so the limit as I approach 3 of f of x, what's that going to be? All right, well, here's my table right here. Okay? I've got values to the right and to the left, just like we've been doing. So here, limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. Okay. So somebody help me out. If I were to plug in 2.9 into this function, we already know that 3 is not going to work, but I want to see what's happening as we get closer. What should I be getting? I need 2.9 plus 3 divided by 2.9 squared minus 9. Aiden? Okay, get negative 10. Perfect. Now I need 2.99. 2.99 plus 3 divided by 2.99 squared minus 9. Okay, when you got it, just shout it. Negative 100. Okay, 2.999. Negative what? Negative 1,000. There we go. So does this look like it's approaching a specific number like the previous ones have been doing? No? So it looks like they're just getting, what, larger or smaller really fast? They're getting smaller. So I would say this limit is approaching negative infinity. They're going to continue to get smaller without bound very, very quickly. Okay. Has anybody started to figure out the other side? What's 3.1? 10. 3.1 plus 3 divided by 3.1 squared minus 9. Now 3.01. 100. 3.001. 1,000. So it looks like as I approach 3 from the right, it looks like the y values are increasing without bound. So what would I put here for the limit on the right? Goes to positive infinity. Okay. Dadgum. Figure out who's texting me. All right. Now, what would we say about step number 2? Do I have a limit? Did I approach the same value from both sides? No, I did not. Remember, infinity isn't even a specific number. So that guy does not exist. All right. So we know there's a problem happening at 3. So I'm going to come back over here to my 3 options. Is there anyone that's talking about as you approach an x from left and right, maybe the y values are going to increase and decrease without bound? There you go. It's this one right here, an infinite discontinuity. So I know what's happening here. We have a vertical asymptote at x equals 3. Okay. There you go. Now, this other one right here, I just want to go ahead and show you very quickly. If I were to plug in f of negative 3, can anybody tell me what's going to happen? It's 0? It's undefined. Because even what happens when you square a negative number? It's still positive minus 9, so it's going to become undefined. You can't divide by 0. But just for the sake of time, I'm going to go ahead and plug these in real fast. Negative 0.164 Okay, negative 0.166, negative 0.167. Then this one right here is a negative 0.169, negative 0.167, negative 0.167. You'd be able to see a difference if you took more decimal places. Okay. But what are you noticing is happening on both sides? Are we approaching the same value? Yes. Now, does anybody recognize that decimal value? It is a fractional value. If not, that's okay. It's approaching negative 1/6. Okay. Now, the more you work with these, you're going to gain more experience. So see, we know there's a problem at -3, okay, because it's undefined, right? But in step number 2, the limit may still exist even though there's a problem there. We've seen from the table, from both the right and the left, the limit as x approaches -3 should be negative 1/6. Can anybody tell me what's going on here? How can I still have a limit, but it's undefined at that value? What discontinuity is this? This is a removable discontinuity. Okay. If I were to come back over here, it says if the function is continuous everywhere except for a hole at x equals c. The limit will still exist. You're still going to approach the same y value, but at that x, the function is undefined. Okay, so this is a hole. Now, think about what we discussed over the past couple of days. How do I factor x squared minus 9? X plus 3, x minus 3, right? I'm going to go ahead and show you this very quickly. Okay, well, the fact that I have two groups that cancel tells me there's a what? There is a hole. Where? Wouldn't it be at -3? Okay. Now, because the x minus 3 did not cancel, that means 3 becomes a what? Vertical asymptote. And that's exactly what we found out before we even looked at the function. So that's what the continuity test is helping us with. Yes, sir. So now, see, this is the justification. Okay, because we know at this point, yeah, because we're taking a lot of the shortcuts, but this is what you're going to be expected to do in calculus. And they're going to take it a lot further. There's a lot of different ways to evaluate limits. And if substitution doesn't work, then you got to try another strategy. Because you saw right here, even if I plug in the number, if there's a problem there, can the limit still exist? Yes. Yes, there we go. Somebody said yes. Okay. All right, so I wanted to go ahead and give you a little preview of that. All right. If you do have any more questions, please let me know. Okay, so if you will clear your desks for me, please. Looks like we have 18 minutes, and that's plenty of time because you only have one question on your quiz.